All right, let's start. Good morning. So grades for midterm 1 is up. Like I had suspected, this issue with a sequence converging if and only if its average is converging. xk, this thing. I think this was problem 4. It was a little bit more hard than I was expecting it to be. What I told you is this side is correct. On the other hand, this side is not correct. Because this problem was it was harder than I expected, I graded that accordingly. The average of the exam is around 82. The max is, I think, 93. So beyond this issue, I'm generally happy with your performance. The key is up. I would highly recommend that you do have a look at it. And if you're not quite clear as to how I solve certain problems, I'm happy to talk to you about things. One major issue was, for instance, with this problem, many of you said, oh, if x bullet converges to x star, then this converges to x star as well because this is a subsequence of x bullet. But that is not quite correct. Okay? So in certain situations, you can think of it as a subsequence, but in general, right? So if I have sort of even 1 over n, so imagine x sub n equals 1 over n. Then what are the terms of these? Well, you're going to first tally terms, right? So let's say this is a sub n, nth average. A sub 1 is, well, x sub 1 divided by 1, that is 1. A sub 2 is 1 plus 1 over 2 divided by 1/2, which already is not quite a number you can achieve, right? So this is what? 3 over 2, 3 over 4, for instance. Or the second average is not a position you can attain using the original sequence. All I'm trying to say is that the sequence of averages is not a subsequence of x bullet. Okay? It's an algebraic operation you're doing using the real numbers. With subsequences, all you get to change is the time. Okay, so that was one thing that some of you missed. Another thing that some of you missed was this idea that if you were to look at this set, right? So Q in positive or non-negative rationals such that Q squared is at most 2. I asked what is the sup of this. Many of you, I think almost all of you got that right. Sup is root 2, but when I asked max, some of you said max is also root 2. But in order for max of this set to exist, right? So it has to be equal to sup, but the sup has to be within. But in order for root 2, that is the sup of the set, to be within the set, well, root 2 has to be rational. Okay? So you should have said that the max of this set does not exist. Makes sense? That's the only difference between sup and max. That's why we spend so much time sort of discussing this supremum as something different than maximum. Okay? So this is something you should keep in mind. Of course, you know, for general purposes, max and sup are not really that different. So especially in more applied areas, especially if you're conversing with people who are not that worried about these technical matters, you can kind of use them interchangeably. But in this class, we're supposed to have some sense as to what the distinction between sup and max is. And so you lost some points based on that. Another thing some of you missed, I asked what is the smallest closed interval that contains this. I think many of you did say that the answer is 0 to root 2 closed. But then I asked what is the largest open interval contained in this. Well, you missed the fact that this is a set of rational numbers. And so it doesn't contain any intervals whatsoever. Okay. And indeed, if you look at the selected solutions, this was of course also a problem in one of the problem sets which I wrote solutions to. This idea that given a set of reals, the largest open interval contained in A is this open interval if and only if A itself is an interval. Okay? In this case, certainly it is not an interval, and so it contains no, there's a bunch of like holes in it. You're missing a lot of irrational numbers. Okay? Any comments or questions about the midterm? I've talked to some of you. Some of you said maybe it was too long. Any other sort of comments about the whole thing? Some of you said, oh, I had trouble sort of converting the idea that I had into a rigorous proof. Well, certainly that is part of this course, and because of these kind of matters, I try to be rather lenient about exams when it comes to grading exams. Another comment I received was, well, it wasn't quite clear to me what I could assume and what I could not. That's again a reasonable concern to have. My general idea always is, well, you should act in such a way that I'm aware of the issues that you might encounter. In the sense that, well, depending on how much time you have, you should give a comparable amount of detail. Okay? So, for instance, I prove things in class, and often I sort of like hand wave a bunch of things, but when you look at the selected solutions I write, they're a lot more detailed. Why? Because I get to sit down, I have a lot of time. I don't have a lot of time, but at the very least I can sort of sit down and sort of really think about what I'm trying to say, really try to optimize the presentation and so on. And so in the exam, of course, you have limited time, and I grade the things that you're saying accordingly. And I'm happy to talk about your midterm if you want to sort of go over your work and so on. Or if you have more sort of comments or suggestions regarding the midterm logistics and all those other things, I'm happy to discuss that one-on-one or after class or whatever also. Okay. I should say the fifth and sixth problems, they were worth 5 points in total. I like to give a couple of very hard problems. So for instance, the last problem was really hard. It was really hard, and if you look at the solution, it just like takes me a while, and like it's a trick that you just need to see. And so in each exam, I like to give some sort of like problems for the top of the class, for the very top, but even without those, I design exams in such a way that a student that spends sufficient time and effort with problem sets ends up getting an A, at least in the exam. Okay. One final thing I want to say is that I haven't seen many of you use the extra pages that I've left out, and so many of you just like thought of an idea and started writing down the proof and so on, or whatever you were writing, maybe the counterexample, whatever. But I would suggest writing a proof should be the last thing that you should try to sort of pin down. First, have an idea and verify indeed that what you're thinking should work and so on. Anyway, these are a bunch of comments. Like I said, I'm happy to discuss further. Okay, so integration. Standing assumption, I is going to be a closed and bounded interval from lambda to rho. Recap, as a recap, let's go back to the definition of a step function. These are special types of functions that in the next problem set 2, the one due this Friday, you're going to use quite a bit. Somehow, in problem set 5, you're going to see this other integration theory, Bourbaki integration, that is much more restrictive than Riemann integration. But it's a good practice for uniform convergence and so on, and also pointwise convergence. So that's why that's why I suggested that. That's why I put Bourbaki integration in that problem set. But so a step function is a sigma. It's a function defined on I taking real values that has two specific properties. Namely, it takes finitely many values. So not the inputs, but the outputs. When you plot the graph, it's a bunch of horizontal line segments. And the second part I should say, of course, is that for each height you attain, there are finitely many pairwise disjoint intervals, J1 to Jm, such that the level set is their union. Okay? For sigma, a step function like this, we define the unsigned and definite integral. You can just skip these two words if you want. The integral is going to be, I'm going to denote it using this more standard symbol, is this. And what is going on here? Well, I sample out, I sum over each height. So this gives me the height. Once I fix the height, I have finitely many intervals. And so I just look at the level set. The level set at y is finitely many intervals. Well, I'm just going to add the lengths of each of these intervals. And so this is going to give me something like this. I'm going to add the lengths of each of these. And then I'm going to multiply each of these with the appropriate height, which is this y. And then if I add over all values that sigma attains, then that should give me a reasonable integral for my sigma. In a second, we're going to talk about perhaps a much more convenient way of thinking about step functions. For now, let's take it for granted. So maybe I can do an example here. So let's look at this, for instance. So 1, 2, 3, 4, like this. And then say like this. So this is height 4. And then like so, I'll add this point, and then maybe this point, or this height. Okay? So this is a step function defined from 0 to 4. Okay? As you see, it takes exactly 3 values, namely 1, 2, and 4. Okay, let me write down the definition if you want. So based on this, I have this piecewise expression. Between 1 and 2, it's something else. Between 2 and 3, it's something else. And then after 3, it's something else. So here it's at 1, then it is at 4, then it is again at 1, then it is at 2. Okay? That's a well-defined function. Its image is this finite set, 1, 2, and 4. So the number of things in the image is 3. Okay? Satisfies the first property. And as you see, for each height that I achieve, the level set is the union of finitely many intervals. So for instance, pre-image of 1 is this interval union this interval. So this and this. Union 2 to 3. Okay. Union of finitely many disjoint intervals. Level set of 2, I just look at this, 3 to 4. Level set of 4 is 1 to 2. Okay. So this sigma, as you see, satisfies the first property of a set or of a step function, and it also satisfies the second property of a step function, meaning it's a step function. Okay. Any comments or questions about this? The key to understanding integral calculus, at least in one dimension, is to be able to engineer and designer these nice step functions. So this is a step function. So sigma is a step function. What is its integral? Well, I'm just going to look at the area underneath, essentially. What that says is that sum over the image 1, 2, and 4, 1 multiplied by the length of this, which corresponds to taking this area. 2 multiplied with the length of this, which corresponds to taking this area. And 4 multiplied with the length of this, which corresponds to this area. Okay? Meaning, consequently, the integral of sigma is 1, 2, 3, 4, 8. Okay? No matter what type of an integration theory you're looking into, it's very likely that if you're trying to integrate a step function, first of all, step functions are going to be integrable with respect to whatever your integration theory is. And second of all, its integral is going to be defined like this. Okay? Or something similar to this. Any comments or questions about this example? Yes?
I noticed that the endpoint, sometimes it's alternating, right?
Yeah, so the endpoints are not really, I don't need to worry that much about the endpoints, because even if, so imagine this. Take, for instance, this endpoint and move that somewhere else only. Everything else is the same. That would be a different height, but okay, so it's a different step function, but ultimately when I try to compute the integral, which is my main concern, that height I'm going to multiply by the length of the corresponding level set, but if it's only a point, well, that interval is just a point, so its length is 0. Okay? So if you were to, in other words, if you were to take a step function, something like this, and adjust its values at most finitely many points, integral is not going to change. This expression is not going to change. Because you're just adjusting heights. You might well be adjusting the heights, but the corresponding lengths of the intervals are going to be 0. You're adjusting the set, you're adjusting the step function on essentially a set of 0 length. And so this is a very important property of an integration, of most integration theories. Somehow, once you take integrals sort of hide away the blemishes and so on. Okay. I'll say more about these step functions. And in a sense, I've already sort of given you a hint as to where we're going in a sense. Ultimately, because these step functions I'm just using as sort of like an aid, and what I really worry about is the integral that I associate, this number. We're going to sort of bypass step functions altogether and transition to what are called partitions. This is what they use in all the notes or textbooks that we're looking into. But it's going to take a while. Before that, I want to define Riemann integrability. So if I have a function f on my interval I, then I get to define these lower and upper Riemann integrals of f like this. And so when I look at the lower Riemann integral, I'm going to have this integral expression, but to the left of it, as a subscript, I'm going to put an r with an underscore. Underscore means it's a lower integral. In the textbook, you would, so in Taylor, this expression is denoted like this, I believe. Okay. In Taylor. And this would be denoted by the same notation, but you would put an over bar, overline on the integral. And so how do I define this? This is the number that is supposed to be the lower Riemann integral. By the way, these are extended numbers, but never mind. Forget about the soup for now. This is a set of numbers, okay? General elements, the condition, okay? Set builder notation. Okay, I'm going to take an arbitrary step function such that for each x in I, sigma of x is less than or equal to f of x. Meaning, when I look at the graphs of f and one of these arbitrary step functions, the graph of the step function is always beneath the graph of f. For each such step function, I get to associate a number, which is this integral, which is this number. And then, as I vary step functions, I have a bunch of different numbers like this. So ultimately, this is a set of extended numbers for me. Well, then I take the soup of it. And so this is a common sort of pattern in analysis. You always do minimax or maximin, okay? First you say, okay, I'm going to try to kind of approximate f from below using a step function. Then out of all these lower approximations, I'm going to take the best one. Okay, very similar idea to sort of even the definition of the soup. This is the lower integral. Upper integral, you do it the other way around. You take an arbitrary step function, this time tau I called it, such that its graph is always above f. Then, given any such step function, you look at the integral of that step function, as defined before. That gives you a set of real numbers. Then you optimize. And that gives you the upper Riemann integral. Okay, so for the lower Riemann integral, you do maximin. For the upper Riemann integral, you do minimax, essentially. Maximin, minimax. Okay. Well, given these two, now maybe I should give that as an exercise. The lower Riemann integral is always going to be less than or equal to the upper Riemann integral. All right, here, I'll erase this. Exercise. For any f, the lower Riemann integral is going to be always to the left of the upper Riemann integral, which in principle could be infinity. Well, I'm going to call f Riemann integrable, and I'm going to call its Riemann integral insofar as these two numbers end up being the same number. Okay, and that's the definition of Riemann integrability. I take an arbitrary function f, then f is Riemann integrable if the lower Riemann integral and the upper Riemann integral are equal and they're both a finite number. In this case, the common number is called the unsigned and definite Riemann integral of f, and is denoted by r to the left to represent Riemann integration, and then the standard integral symbols. Now, I decided to be explicit about the sense in which I do the integrations in class, but in practice, you would just drop your sense of integration at some point if you want to be fast about things. Okay. The set of all Riemann integrable functions on I, I'm going to define by r, I, comma r. Set of all Riemann integrable functions on I. Okay. Okay, so this is a certain subset of the set of all functions defined on I. What I want to say, in fact, is that any Riemann integrable function is, in fact, bounded. Let's do this, and then we'll look into a couple examples. I can just write it like this. The set of Riemann integrable functions on I is a subset of the set of bounded functions. Okay. How can I do this? It's not very hard using the definition. Once you're comfortable with opening up these soups and nymphs and all that stuff. But the idea is this. If f is Riemann integrable, I'm just going to write this to represent, okay, f is a Riemann integrable function, suppressing I and r here. That means that there's a Riemann integral that is well defined. Then the lower and upper Riemann integrals exist, and they're equal, and it's a finite number. Then okay. Well, I'm saying that this soup is a finite number, and this inf is a finite number. Let's call that finite number, in fact, something. Let's call it alpha. Alpha is the integral of my f. Opening up the fact that alpha is a soup of a certain set, well, I have that for instance, epsilon equals 1. I don't really care that much. Then there is two step functions, sigma and tau. Such that for any x in I, sigma is under f, and f itself is under tau. With the property that alpha minus 1 is upper bounded by the integral of sigma which by definition is less than or equal to alpha. This itself is less than or equal to the integral of tau, which itself is upper bounded by alpha plus 1. And so I use the fact that alpha minus 1 is not an upper bound for the set, which gave me a step function, sigma. And likewise, I use the fact that alpha plus 1 is not a lower bound for this, again by the definition of the if, which gave me another step function. I'm not going to use this inequality that much. Really, I'm going to use this. Because any step function it takes finitely many values, which in particular means they are bounded. Well, if this is bounded and this is bounded, well, I get to bound f using these also. Then min of sigma, which is a finite number, lower bounds any sigma of x, which lower bounds any f of x, which lower bounds any tau of x, which lower bounds or which is upper bounded by max of tau, which itself is a finite number. Meaning, I was able to bound from below and from above any f of x by expressions that don't depend on x. That means f is bounded. Okay. Any Riemann integrable function is bounded. So if you were to think about something like this, from 0 to 1, let's say, probably you know how to compute this integral. But for now, we actually don't know how to make sense of this. Even if this has a valid finite value, you would just take the antiderivative and evaluate it at the endpoints and whatever. Well, this is not quite something that we defined yet. This is an improper Riemann integral, for instance. For now, we can't make sense of this expression and we can't compute it because it is not bounded. There's a blow-up. OK. So at this point, I think it's a good idea to come up with an example of a Riemann integrable function and then compute its integral more specifically. And then I think it would be a good idea to come up with an example of a bounded function that is not Riemann integrable, so that this inclusion is proper. Not all bounded functions are Riemann integrable. Even before that, just to give you, just to provide you some examples, and connect it to Bourbaki integration that is part of problem set 5. Any Bourbaki integrable function is Riemann integrable. And Bourbaki integrals and Riemann integrals coincide for Bourbaki integrable functions. B of IR is a subset of R of IR. Bourbaki integrability implies Riemann integrability, which in particular means any monotonous function, any continuous function, any piecewise continuous function is Riemann integrable. So I'll write it in words as well. I.e., any Bourbaki integrable function is Riemann integrable, but not vice versa, actually. But let me just finish this. Integrable In particular, C0 is in R. Any continuous function is in Riemann integrable functions. Any continuous function is a Riemann integrable function. I'll leave that as an exercise also. This is a very nice exercise. Not all Riemann integrable functions are Bourbaki integrable. It's a great exercise. Just to remind you, what is a Bourbaki integrable function? It's a function that is the uniform limit of some sequence of step functions. I'll remind you that here. So recall f is in B if there is a sequence of step functions such that sigma bullet converges to f uniformly. That's the definition of Bourbaki integrability. I should mention, I said it out loud, but I didn't write, any Bourbaki integrable function is Riemann integrable, and for any Bourbaki integrable function, the Bourbaki integral coincides with the Riemann integral. I'll write that too. For any f and b, Bourbaki integral is the same thing as the Riemann integral. Okay, so here are examples. Let's do this. You want to keep the examples very simple, okay? Otherwise, it's going to get nasty. So within this more abstract point of view, you want to keep sort of building new tools that apply to classes of functions that you can use, as opposed to taking one complicated function and try to integrate it using the definition. If you're going to try to understand the definition, so if you're going to try to apply the definition and compute something, you want to keep that example rather simple. So let's say f is just the x function, diagonal. This is a continuous function. By the exercise, it is Riemann integrable. The point is to compute its Riemann integral. Okay. If you want to compute, the Riemann integral of this, what is the integral of this function from 0 to 1? One half? Yeah. If you can guess what the integral of a function is, probably that is the integral, okay? How can you do this? Well, assuming Calc 1 works, you would say, oh, x is the derivative of x squared divided by 2, and then probably there's a fundamental theorem of calculus so that I can shed that derivative. And so I need to evaluate x squared over 2 from 0 to 1, and that gives me 1/2. You can do it that way. You can plot the graph. To realize the graph of f, or rather the area underneath, is nothing but a triangle. Assuming that Riemann integrals are intuitive, the integral of this function should be the area underneath, and the area underneath is the area of this triangle, which is a right triangle. 1 times 1 divided by 2 is 1/2. You can do it that way too. Of course, these are heuristics. You have a candidate for the value. Now, the point is to figure out how to actually rigorously verify this. Okay. Well, I'll try to draw a bigger picture. Something like this. Well, I want to design a sequence of step functions that basically close in on f, right? from within and from without. What I can do is, well, I can just split it into two, for instance. And then here's one step function, like so. Okay. The integral of this step function would approximate from within this Riemann integral. And then I can look at this guy. So let's say this is sigma 1. Yeah. So sigma is from within, and then I'll have another one that approximates from without. Tau 1. Okay. I don't even need to care about what is happening at the endpoints. I say, okay, on this subinterval it is like 0. I don't want to even talk about what is happening at the endpoint because it's not going to matter when it comes to the the integral. But in any event, the integral of sigma 1, okay, is what? This is 1, 1, 1/2, 1/2. What is the integral of sigma 1? Right, so how many different values does it take? 1/2 and 0. 0, I don't need to care anything. I don't need to care about. 1/2, I look at the length of the level set. It is 1/2. 1/2 times 1/2 is 1/4. Okay. And if you were to do the same thing with the other guy, it says, oh, this time I'm taking two heights, 1/2 and 1. 1/2 I need to multiply with 1/2. 1 I need to multiply by 1/2 also. So that is 1/2 plus 1/2 times 1/2. One over 4 plus 2 over 4 is 3 over 4. Okay. So you see, this number undershoots the target. This number overshoots the target. Okay. Now we keep going. Split it again. I'll do one more picture over here. You see, I like subdividing into equal pieces like this, especially for functions that are like very nice and symmetric. That sort of ends up being, convenient to write down explicitly. So at this stage, what we can say is this, okay? Because the lower Riemann integral is the sup of all such expressions, I can say that the lower Riemann integral of f is lower bounded by 1/4, and the upper Riemann integral of f is upper bounded by 3 over 4. I can write that. So so far, we have these estimates, in fact. What I want to do is I want to keep sort of partitioning my domain into smaller and smaller pieces to come up with, to engineer better step functions that sort of like wrap around the graph of f tighter. And hopefully, by doing this way, I'll be able to lower this upper bound and increase this lower bound. I'll do one more. So my function split into, instead of 2, split into 4 this time. Okay. So I'm going to look at this now. This is my sigma 2. Okay. And then the other one is going to be from without. Okay, let's compute the integrals of these also. well, sigma 2 takes 1, 2, 3, 4 distinct values. Okay, I don't count this. 1 over 4 times 1 over 4, 1 over 2 times 1 over 4, and so on. So this is 1 over 4 times 1 over 4 plus 2 over 4 plus 3 over 4, whatever this is. Okay? Because ultimately, I don't really care at this stage that much about the exact values. I'm trying to come up with a pattern so that I can look at sigma n and tau n and come up with formulas like this. What is this? Again, I need to multiply by 1 over 4 each of these heights. They go from 1 over 4 to 1. Okay. Again, this is some number I don't really care that much about. In any event, though, at the very least, one thing I can say is, well, this is going to be larger than the integral of sigma 1 over there. Okay? So it's a better approximation for the lower integral. And likewise, this is a better approximation for the upper integral. And you see, I'm trying to squeeze these together. So tau 2, tau 1. Okay, what is the general situation then? If I had an n, okay, I would have the staircase that is underneath the graph of f, sigma sub n, and another staircase, tau sub n, that is above the graph of f. Okay, so looking at these, I can say that the integral of the nth under lower staircase should be what? Well, each of the lengths of these intervals is going to be 1 over 2 to the n. And how are the heights? How do the heights vary? Well, they go from 0 to 1 over 2 to the n, 2 over 2 to the n, all the way up to 2 to the n minus 1 over 2 to the n. Okay, I can come up with a closed formula for this, because this is 1 over 4 to the n times the sum of integers from 1 to 2 to the n minus 1. We know that's that formula. This is this plus this times 1. So this times the number plus 1 divided by 2. So this is 2 to the n minus 1 times 2 to the n divided by 2. That's an approximation. Okay. It's a lower approximation for the integral of f. And as I take n to infinity, well, these are going to basically cancel each other out by whatever rule that you want to look into. And this is going to converge to 1/2. For instance. Make sense? And you do the same thing with the tau. You sort of look at tau sub n, same type of a function, staircase from above, sort of 0 in. Again, it gives you a formula like this when you look at the integral. You take the limits as n goes to infinity, and that gives you this. Okay. I'll leave it to you to finish doing this because we're out of time. Finish the calculations. Okay, good. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. I'm happy that you're here. So in the morning, I didn't see anything out of the ordinary, but as time goes by, things might get worse. regarding the weather. So thank you for showing up. So we have a couple of things to discuss. I wanted to give you a broad overview as to where we are. So we're in week 7 currently. We're slightly behind schedule compared to the tentative schedule on the syllabus. What we might end up doing is you might end up getting rid of the topics for the next week. Those are sort of more advanced things in a sense. And we'll just sort of figure out what to do, because I'm happy to just focus on certain parts of these integration theories as opposed to everything that is written in the textbook. So, as usual, for integral calculus, the main habitat is a closed and bounded interval. So I is always going to be like that. And at this stage, we have a bunch of different classes of functions or sets of functions that I wanted to mention. So in analysis, in calculus, this is a very important thing to be able to do. We have different properties: continuity, integrability, monotonicity, whatever, a function being a step function, and so on, which means that each of these is a set of functions, okay? And so every once in a while, it's a good idea to try to draw some sort of a map in terms of a basically Venn diagram that describes inclusions and exclusions and intersections and so on. So here's the legend, okay? I didn't write down the domain and codomain of these spaces, but for instance, F there stands for the space or set of all functions. So all functions from I to reals. F sub B, it may not be very clear from this picture, but it's certainly a subset. So it's a smaller blob. These two were sets that we had introduced fairly early on. And then we talked about continuous functions. And remember, we had this maximum principle that said that any continuous function defined on a closed and bounded interval is automatically bounded, which means that this blob that represents continuous functions should be a smaller blob inside the blob that represents bounded functions. Okay, so that's what I mean here. What else? R we define, or maybe even before that I should mention B, Bourbaki integrable functions. This is in the problem set due this Friday. And yesterday I gave you this exercise that any Bourbaki integrable function is Riemann integrable. And for a Bourbaki integrable function, Bourbaki integral and Riemann integral coincide. So you don't get two distinct integrals for those. But in any event, if R represents the Riemann integrable functions, we showed yesterday how Riemann integrable functions are bounded. And I gave as an exercise that Bourbaki integrable functions are Riemann integrable. So like the blob corresponding to Riemann integrable functions is sort of somewhere in between. What else? In the problem set due this Friday, you're going to show that continuous functions are Bourbaki integrable. Certainly step functions are Bourbaki integrable. Monotone functions are Bourbaki integrable. You're going to show these. And how are monotone functions and continuous functions situated? Well, both of them are blobs inside B, and they have an intersection. You could have monotone functions that are continuous, but there are also discontinuous monotone functions. And there are also continuous functions that are not monotone. Okay? So you have some functions here, some functions here, some functions in between. And you have step functions that are both continuous and monotone, which is the case when the step function is constant, in fact. Or you could have a step function that is discontinuous but monotone, or you could have a step function that is neither continuous nor monotone. So this represents that. So just keep the color codes as well. Blue is monotone, so non-increasing or non-decreasing. Well, step is clear, all step functions. What else? This probably you're going to encounter in the next problem set. This is what is called the bounded variation functions. With bounded variation. And probably one exercise, one problem is going to be to show that any bounded variation function is Bourbaki integrable. There's a question mark here because I might be missing something. Maybe any Bourbaki integrable function is also bounded variation. I doubt it, but maybe this green blob is, I drew it wrong. Maybe it should have sort of like a part outside or something. Oh, well, I guess it cannot be outside because any bounded variation function I know is Bourbaki integrable, which you're going to learn also in the next problem set. What else do we have? These two, the red ones, these are going to be the two additional integration theories that we're going to discuss. HK is the Henstock-Kurzweil integration or integrable functions, and L is the Lebesgue integrable functions. We're going to discuss these later. So Lebesgue, that's with a G, integrables, and HK is Henstock Kurzweil integrals. Okay. We're going to cover these probably on Friday. This probably we're going to see on the next problem set. Okay. So it's always a good idea to compare properties. This implies that, that implies the other thing. And whenever you see, you sort of verify an inclusion, for instance, yesterday we showed that any Riemann integrable function is bounded, you want to ask the other way around as well. Is it the case that any bounded function is also Riemann integrable? If not, you want to come up with an example, okay? So that this Venn diagram kind of makes sense. So for instance, the reason why I drew it like this is because, well, there is something here, meaning there is a Lebesgue integrable function that is not bounded, for instance. This picture kind of represents that for me. Or there's an HK integrable function that is not Lebesgue integrable, and so on. Okay. It's always a good idea to draw your map and populate, find a bunch of different examples. And this is very important in analysis. Because in a sense, these different function spaces is the main export of rigorous analysis to applications. Depending on the application, you end up needing to use a different class of functions, essentially. Okay? Any comments or questions about this? And maybe you may want to draw this by yourself and try to sort of draw it better or something. Yeah?
I know the function can be defined not in the interval, right?
Yes.
With epsilon delta, we can make function that is not defined on an interval.
What do you mean that is not defined on an interval?
Like a pointwise, right?
Yes, okay.
But you're talking about defined in the infinite.
Yeah. All of these are functions from this closed and bounded interval into reals. Without this closed and bounded interval assumption, this picture is not correct. Because continuous functions need not be bounded in general. They are bounded on a closed and bounded interval, maximum principle. Okay? Yeah, I didn't want to write F, IR, FB, IR, and whatever because there isn't that much space.
So do you mean that continuous function can be unbounded?
1 over x.
But you put that figure inside the bounded.
For this.
Oh.
Yes, that's what I mean. All of these, even though I didn't write it because there isn't that much space, these are all spaces of functions from a closed and bounded interval into reals. Okay. Yeah. Does that kind of make sense? Yeah. Any other comments or questions? So I want to then give an example. So we had given one example of a Riemann integrable function yesterday. We also computed the integral. And in fact, when you think about it, that sequence of sort of staircase functions converged uniformly to the diagonal function, and I was actually taking the Bourbaki integral. It just happens to be the case that for Bourbaki integrals, integrable functions, Bourbaki integrals are easier, or they're equal to the Riemann integrals. But here's another example, okay? This is the classical example of a bounded function on a closed and bounded interval that fails to be Riemann integrable, okay? So it's defined on 0, 1, and it takes the value 1 if x is rational, and 0 if x is not rational. And I claim that f is bounded, but not Riemann integrable. So it's in the complements. Okay? It's clear that this is bounded. It takes only 2 values. It's bounded by 1 if you want. I want to show that its Riemann integral does not exist. What does it mean for a function to be not Riemann integrable? Well, it means that even though lower and upper Riemann integrals exist, they are not the same. i.e., lower Riemann integral is strictly less than the upper Riemann integral. Okay? Lower and upper Riemann integrals exist for any function. Okay? You don't even need to assume bounded. Of course, in principle, then they could be extended values. But in any event, my condition for Riemann integrability is lower integral equals upper integral. Well, if I want to show that this function is not Riemann integrable, I need to show that lower integral undershoots upper integral. Now you open up the definitions. What is this? Okay. By definition, this is the soup of a certain set. It's a soup of a certain set of integrals of step functions. Right? So I take a bunch of step functions that are under f. In Turnstau's notes, I think he calls this, or step function minorizes f. If you want, you can use that terminology. And what is the, oh wait, this is the lower integral. Because I'm approximating from within. Upper integral is the other way around. Inf of integrals of steps, sigma step, and this time it's from above. Okay? So I need to compute these. There are multiple ways of doing this, but in this case we can explicitly compute both of these integrals and show. I claim that the lower integral is 0 and the upper integral is 1. Okay? That's what I claim. lower integral is 0, upper integral is 1. Consequently, they cannot be the same. Consequently, this function is not Riemann integrable. And what is going to be the driving force here? Well, it's this idea that this function jumps between 0 and 1 very often. And somehow we're going to try to use the density of the rationals. Okay? So let's try to go for the lower integral. Let's try to compute this. First of all, what I can say is, and here maybe I can try drawing the graph of f as well. It's kind of bizarre to draw this graph because somehow it's both this and this, sort of like jumps quite often. Okay, this is the graph of f. But if I were to take the function that is constantly 0, that's a step function, and its integral is 0, meaning 0 is in this set. Since the lower integral is the sup of this set, well, lower integral is lower bounded by 0. So x sent to 0 is a step function. Certainly it is underneath f, which means 0, which is the integral of this step function. I'll call this sigma underline. I have this. I have a lower bound as to the lower integral of 0, but I want equality. Well, how do I show that something is the sup of a set? Well, there are multiple ways of doing this, but here's one way. I can take an arbitrary step function that is underneath the graph of f, and based on that, try to come up with an estimate as to the integral of that step function. So let sigma be an arbitrary step function such that for any x and I, sigma of x is less than or equal to f of x. Okay. I want to somehow argue that the integral of this sigma cannot be greater than 0. Or in other words, it is upper bounded by 0. Here's one way to do this. I take one height in the image of my sigma. They're only finitely many by definition. The level set of sigma at height y is the union of finitely many pairwise disjoint intervals. Say there is one of those intervals that has positive length. Say there's an interval j sub I in the level set such that the length of this interval is positive. Okay. Well, then by the density of rationals, or I can do that, I can do that. By the density of irrationals, that's easier. By the density of irrationals, there is some point that is here that is not a rational number. Then there is, well, I'll put it this way. J sub I, take away rationals, is non-empty. Okay. And in fact, I'll do it like this. Then there is some x in j sub I, take away rationals. But then, on the one hand, I know that on this j sub I, sigma takes only the value y. And simultaneously, sigma of x is upper bounded by f of x. But f of x, when x is irrational, is 0. Then y equals sigma x is less than or equal to f of x, which is exactly 0. Okay. So this height that I chose in the image of the step function is upper bounded by 0, assuming that its level set contains at least one interval of positive length. When I look at the integral of sigma, I have expressions of the form y times the length. And so either one of these intervals has 0 length, which doesn't contribute anything to the integral, or if it has positive length, then the height has to be negative or non-positive. This means that the integral of the sigma has to be upper bounded by 0. Okay? And so that concludes it. So the step function that is constant to 0 is certainly within the set. And for any other step function that is underneath, the integral is upper bounded by 0. That means that the sup is 0. In a second, we're going to switch over to a different formalism. Namely, we're going to start using partitions as opposed to step functions. While step functions are a lot more intuitive in a sense, especially if you're trying to control the geometry of the thing that you're looking into, somehow, if all you're worried about is computing integrals, lower, upper, whatever, it ends up being more useful to use partitions. For now, I realize this argument kind of can be confusing, because how does this interval depend on the level set, whatever? Okay. But this is a perfectly valid argument. And by the same argument, essentially, you can show that the upper integral has to be 1. The function that is constantly 1 is a step function that approximates from above, or that dominates f here, and its integral is 1, which means that the upper integral is upper bounded by 1. And then you would show that if you had an arbitrary step function whose graph is above the graph of f, then its integral has to be greater than 1. Essentially by the same reasoning. And in fact, I'll leave that to you. This to you. And consequently, you see, even though this is a bounded function, it is not a Riemann integrable function. There are bounded functions that are not Riemann integrable.
So is there a possibility to integrate it at all?
No.
When
Oh, okay. So, okay. Fair enough. So that function we're going to see, in fact, is here.
outside Riemann integrable.
Yes, it is outside Riemann integrable, but once we define these, we're going to see that it is both Lebesgue integrable and HK integrable. And with respect to HK or Lebesgue, we're going to say that its integral is 0, in fact. Yes. Very good. You had a question? No? Yeah, so just to summarize, so the Riemann integral of this specific function does not exist. It's not defined. Okay? But later on, if instead of this R, if you put L or HK, we're going to learn these different types of integration, this is going to come up as 0. What is the idea? Well, the idea is most numbers are irrational, and therefore, even though you have a bunch of like these oscillations, it actually shouldn't count. Okay? We'll see all that later. So in probability, this function would be called the indicator function of the set of rationals. And so in probability, subsets are thought of as events, and the integral of this function would be the probability of that event happening. In other words, the probability of choosing a point that happens to be rational if you were to choose it randomly. Okay. And so somehow, even though the Riemann integral doesn't work, we need some sort of an integration theory that tells us that this is integrable and its integral is 0. Any other comments or questions? Okay. So this definition I gave you for step functions, or using step functions in general, it's kind of cumbersome. This thing is like if I were to choose y, okay, so I have finitely many heights that my function attains, and if I were to choose a height, well, there are finitely many intervals that are disjoints whose union is the whole level set. That's kind of cumbersome to think about. And when you think about it, in the definition, the number of intervals for each level set itself is a function of the height. And then these intervals are not actually uniquely defined. So it's not very convenient. So we're going to transition to this different formalism. And this is also the formalism that even Terence Tao and Taylor's book and Fonda, they all sort of really talk about. What it is that it's kind of more scary thinking about partitions, as far as I'm concerned, compared to thinking about step functions. Okay. I have about 22 minutes for the rest of this class. Probably we're just going to keep defining things. My aim is to define partitions, sampling functions, sampled partitions, Riemann sums. I want to define formally Riemann sums, lower and upper Darboux sums. These are all sort of tools that are very useful. And then if time permits, I'm going to state a theorem regarding certain characterizations of Riemann integrability. You mean probably not, we're probably not going to be able to prove that theorem though, today at least. Takes a while. Okay. Now, for a while, forget about functions, trying to integrate things. My interval is still lambda rho though. Okay? A partition of I, partition, like this, I should write it like this, finite interval partition. Okay? We're just going to say partition, but in reality, the idea of a partition is something more general. We're really using what are called finite interval partitions. Partition of I is a collection, which I'm going to denote like this, curly P. So this is a subset of the power set of the interval. It's a collection of subsets of I, such that well, first, it's a finite collection. So in P, there are finitely many subsets of I. Each subset in P, each element in P, is a subinterval of I. And in fact, it's a closed and bounded subinterval of I. For each P in P, P is a closed and bounded subinterval of I. Three, if I were to take the union of all p's in curly p, well, I get the whole interval. So I get the partitioned interval. I can write it like this. Union over all p's gives me I. Okay, so this is like flat p in a sense. These are like elements in my collection, and the collection is curly p. And finally, if I were to take any two elements in my partition, I want their intersection to be minimal, meaning they should intersect at most at the endpoints, meaning the number of elements in the intersection should be at most 1. So there are no overlaps that has positive length, if you want. Okay, I'm going to denote by par of I the collection of all such p's. Like this. All such partitions. Okay. Now, in the fourth problem set about continuity, you saw this idea of a directed set and nets. Somehow Riemann sums and these lower and upper Darboux sums are going to be nets parameterized by this set. We're going to define certain direction relations on this. Okay, and we're going to take net limits in a sense. We'll get there later. For now, I just defined this collection of partitions. And in fact, this. Here's an example. Now you see, I didn't say anything about the lengths of these p's in my partition to be the same, whatever. This is why this integral calculus is somewhat hard to parse, I think. Okay, I'll leave this. So for instance, example, I is 0 to 1. So p could be like this. 0 to 1 over 2, 1 over 2 to 3 over 4, and then say 3 over 4 to 1. Okay, that's a partition. You see, this is a collection of subsets of I. It has 3 elements. Let's call these P1, P2, P3. What else? Each element in curly P is a closed and bounded interval. If I were to take the union of these, I get the whole interval. And if I were to take the intersection of any of them, any two of them, so these two are intersected. Their intersection consists only of 1 over 2. The intersection of these two consists only of 3 over 4. And if I were to try to intersect this and this, I would get 0. So this is an example. Now, you may want to think about partitions not in terms of these collections of intervals, but rather the separation points. Okay? And so instead of writing it like this, you can just think of it like this as well. 0, 1, 1/2, 3 over 4. That's one way to visualize. Okay? Now, conceptually, I find I prefer this more because this generalizes to multivariable and so on. And the way I think about a partition is really a pixelation for me. Okay? And each of these p's and curly p is a pixel for me. And so I'd rather think about the pixels, this, 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 as opposed to where the pixels are separated. In one dimension, clearly it is very convenient to think about where pixels are separated, but when you think about like even two dimensions, separation of pixels ends up being sort of like a nightmare to think about in a sense. Okay? So for calculation purposes, it's better to think about the cut points. Okay? But conceptually, I want to keep it sort of without any indices. Does that kind of make sense?
So does the intersection become an empty set?
Yeah, so if I were to intersect P1 and P3, the intersection would be 0 or empty set. And so there would be no elements. But you know, what I'm saying is that I'm allowing some intersection, but the length of the intersection should be 0. So even though, in principle, there could be intersections, from that intersection, I don't want to have multiple contributions in the integral. That's why, ultimately. Okay. Any other comments or questions? Okay. So this is this. Let P be a partition. Okay, when I say partition, it's always a finite interval partition. In more general contexts, you allow more complicated subsets, but this is all we're going to use for no matter what the integration theory we're going to look at. Okay, a sampling function adapted to P is a function, which I'm going to denote by S, that goes from the partition itself into the interval, such that for any P in P, S of P is in P. I'll denote the collection of all sampling functions adapted to one specific partition, P, by S of P. Oh. S of curly P the collection of all sampling functions adapted to curly P. Let's give an example. This is my partition. Let's try to come up with a sampling function. So S is going to go from the partition itself into the interval. Say S of P1 is 0. S of P2 is 3 over 4. S of P3 is, let's do something slightly interesting. Let's say the average, 7 over 8. Okay. So the sampling function takes an interval, one of these pixels. To each pixel, it associates one point in the interval. The only condition is S of P1, 0, has to be within the first pixel. This has to be within the second pixel. This has to be within the third pixel. Okay? Meaning, you have your partition. Okay? How do you think about this? This says, oh, for the first pixel, sample this point. For the second pixel, sample this point. For the third pixel, sample the midpoint. That's your S. Yeah.
So you sample once.
Exactly. Yes. To each pixel, you associate one actual point. The way I'm imagining this is that once I have one of these partitions, that is sort of like a lower resolution visual for my interval, I'm sort of only able to see this whole thing as one thing, this thing as one thing, and this thing as one thing. Somehow the sampling function is the more abstract thing where you also say, oh, there's an actual point somewhere that I'm looking into. That's what you say also. Okay. A sampled partition is a partition together with an adapted sampling function. Sampled partition is a pair curly p comma s, where p is in par, it's a partition, and s is a function it's a sampling function adapted to s, adapted to p. Yeah.
Are there any restrictions in sampling the same point that lies on the intersection of
You can. It doesn't matter. Yes. What your colleague is suggesting is, here's another sampling function. So there's an intersection here. If you want, what you can do is, so let's say t, new sampling function. Send p1 to 1/2. Send p2 also to 1/2. Send p3 to 1. So because p1 and p2 has this common point, your sampling function might be sampling the same point for the two intervals. Okay? But to each pixel, you need to have exactly one point, not vice versa. So this t samples this and this. That's also a valid sampling function. Very good. Sampled partition is a partition together with a sampling function, p comma s, and the collection of all sampled partitions I'm going to denote by sPar. The collection of all sampled partitions. Okay. Any comments or questions so far? Now, this notation for par and sPar, even this name of sampling, these are not sort of industry standards. There are like multiple different names. Some people call this a tagging. Instead of partition, people call this a division. Like depending on the textbook, there's like different terminology. We're just going to stick to this. I mean, at least I will. I'll make a connection between the step functions and partitions or sampled partitions in a second. I want to define Riemann sums formally. So you see, so far, there was nothing, I didn't mention anything about a function that we were trying to integrate. So now I take an f. Let f be an arbitrary function. Then for any curly p comma s, a sample partition in I, define the associated Riemann sum to be the following. associated Riemann sum to be, well, I'm going to denote it like this: R, F, comma, P, comma, S. Okay. Sum over all pixels. Apply F to each of these sample points. This gives you the height information times the length of the pixel. And how do I think about this? Here's sort of one way to visualize what is happening here. Say this is your function. Okay. Take a partition like this. Okay, that's your partition. Take a sampling. Say this. Let's say this point, let's say this one. Okay, that's your sampling function. What is happening here? Well, I'm imagining this S points to be something like vertical grappling hooks. Okay, you sort of like shoot an arrow vertically, and you keep track of it until you hit the graph of F. You say, oh, that is my height now. You see? So for this is P1, this point is S of P1. If you apply F to it, you get this height. So this is your height information. And so you multiply it with the length of the corresponding pixel. Okay. And shoot up, add this, shoot up, add this, the area of the rectangle, and finally shoot up and add this area. That Riemann sum is the area of this green area. Okay. So you see, this depends not only on the partitioning, but also on the sampling function. If I chose a different sampling function, imagine moving this arrow this way, well, the area then, based on this specific function, would decrease. Because even though the base height is the same, I'm changing, or sorry, the base length is the same, I'm changing the height this time. So this, you see, depends on F certainly, but also on the partition and on the sampling function. What we're going to do is, well, ultimately we're going to think of this expression as a function of P comma S, okay? So that's going to be a net for us. And we're going to take the limit of this expression as PS goes to infinity, whatever that means. Depending on how we take that PS to infinity, we're going to get different notions of integration. I have 1 minute left. I think I don't want to keep pushing. There are two more sums, lower and upper Darboux sums, that are very relevant, but I'd rather define them on Friday. Thank you. All right, let's start. Good morning. So today I'm going to take attendance. We're going to keep working on integral calculus. I'm going to define a couple of things associated to partitions, state a couple of exercises which are probably going to show up in the problem set I'm going to release today. I'm going to release problem set 6 later today. It's going to be mostly about integration, specifically Riemann integration this time. And hopefully we'll also prove a certain theorem about characterizations of Riemann integrability that's going to sort of open up for us a whole new world of gauge integrals, in a sense, because we're going to take one of the characterizations and we're going to sort of generalize it somehow. Now, as usual, setting assumption is we have an interval I, closed and bounded, and we're always looking at functions on closed and bounded intervals. Now, in principle, you can generalize this as well, and by now I hope you would agree with me that, you know, if I could, I would. But there's a reason why I'm not doing this, because if we try to generalize this to more complicated subsets or more complicated spaces, the nature of the theory really changes. So specifically, either you would need to sort of make sense of integrals over unbounded domains, which if time permits, we're going to try to handle, or you need to sort of come up with an idea as to what sort of a space allows you to integrate functions over. So for more general stuff, either improper integrals or this other paradigm, which is this Lebesgue paradigm, remember. And we're not sort of discussing that. Or Lebesgue paradigm. So if you try to sort of come up with a theory that is more general than this, which certainly is useful and people did do it, but somehow the nature and the flavor of arguments changed so much that I don't think it is worth the generalization. And there are other classes that are really focused on these more generalized situations. And another thing too, as you're trying to read a certain text, whatever, you should always keep in mind what sort of assumptions are being made. Right? So it's all about this logical perturbation and stuff. And you should always ask yourself, oh, is this assumption something necessary, or is it only convenience? Okay, so you always want to keep that in mind. Okay, so if I have a function f on my interval taking real values, remember we had these sPars and pars. So sPar is a sampled partition. So you have an interval like this. Well, you sort of chop it into a bunch of pieces, right? So sort of divide it. It doesn't need to be sort of uniform in length, whatever. As long as you divide this into finitely many pieces, each a certain interval, subinterval, that's a partition. And then if for each of these pixels, you choose one sample point like this, or tag, you might also see, that would be a sampled partition. Okay. So we took all such p comma s's and put them in a subset, so that if you don't consider the s's, if you only consider partitions, you have the set of partitions of I. And so if you want, set of partitions of I is a subset of the second power set. Because any element here is a collection of subsets. Right, so if P, curly P is a partition, if it's an element in the set, that means, well, for each P and P, P is a subset of I. I think this is correct. Yes, which means curly P is a subset of the first power set. Oh, that means, OK, the collection of all such is in the second power set. Not that this really helps, but at least at first, you can sort of make sense of this using the operations we discussed regarding set theory. And likewise, you can sort of make sense of this sPar as well. But of course, it's slightly more complicated to formalize or write it out explicitly what this sPar is, or where it lives in a sense. But in any event, certainly you can consider the collection of all sample partitions, P comma S. And once you have one of these, you can look at the associated Riemann sum. Okay, R of f semicolon p comma s. So it depends on all three of these. And how do you handle this? Well, if you have a p comma s like this, and if this is your function, to each pixel, you associate a length, these. Okay, you have the length. And furthermore, once you have these sampled points, you sort of look at the heights. One height for each pixel. And so to get the area, you multiply this length with this length. And then you add all of these up. This is the standard Riemann sum. OK. On the other hand, if I have further f bounded, then I can also look at more things. Namely, for each partition, now I don't really look at sampled partitions, just partitions. The associated lower Darboux sum and upper Darboux sum and the Darboux aperture are defined like so. Respectively are lower Darboux it's going to be like this. It's very similar to the Riemann integral or Riemann sum. Sum over all pixels. You're going to, again, use the length. But for the height information, what you're going to do is you're not going to use a sample. You're just going to look at the nth of the function restricted to each of these pixels. So here, for instance, you look at this. Here you look at this. Look at this. That gives you the lower. And so this height information I'm going to replace with the nth. Nth of f restricted to this specific pixel times the length. That's the lower Darboux. Upper Darboux is the same, but instead of looking at the nth, you look at the sup. So for instance, for this pixel, you would look at this height, then this height, and so on. That would give you the upper Darboux. So sup of f restricted to this pixel times the length again. And the Darboux aperture is simply the difference between these two. So you look at the base, and then you look at the difference between the upper and lower Darboux sums, which means you're just going to look at these areas, these gaps, and you're going to add them up. Which, if you want, you can also write it like this. When you rearrange everything, this is the diameter of f of p times the length of p. Okay. Now, some terminology. If you look at the Taylor textbook, there he calls these two not the lower and upper Darboux sums. He just calls them Riemann sums. And this is, done in certain textbooks, but historically speaking, these were thought by this French mathematician, Darboux. So Riemann was able to formalize integration using Riemann sums initially. And then after that, another mathematician came around and he said, well, this is too complicated, the samples, whatever. I'm just going to look at inf and sup. And I'm just going to try to come up with a characterization of Riemann integrability in terms of these two. And so historically speaking, it is more accurate to attribute these to Darboux, and that's what we're going to do. The third, this Darboux aperture, sometimes you might see the word variation or oscillation, whatever. But since we've seen those phrases elsewhere, and this is not exactly the same, I just came up with a different name. And it just turns out to be the case that this D often is a lot more useful than U and L combined. And somehow, often you end up needing to prove that this aperture goes to 0, essentially. So the gap between the upper estimate and lower estimate goes to 0. Okay. So here's a nice little exercise. I want you to think about why, for these specifically, I need to assume that f is bounded. Not for the Riemann sum. Riemann sum is fine. But for lower and Darboux, lower and upper Darboux, it's a good idea to assume f is bounded. By assuming that my f is bounded, I'm somehow avoiding certain pathologies here. Okay. So, what else do I want to do? Okay. So here are some exercises that are going to probably show up in the problem set 6. First of all, given any f, all three such sums can be actually actuated as the integrals of certain step functions. Can be thought of as integrals of certain step functions. Okay. So in a sense, underneath the hood, instead of writing these, you can think of these to be of this form for certain step functions. Okay. The benefit of perhaps switching over to this partition formalism is that you're basically cutting the middleman. You're sort of getting rid of this step function because you say, I'm only interested in this integral. Okay. So that's good. What else do I want to say? Okay. This is probably also going to show up in the next exercise, next problem set. See how I wrote this? Okay. Now, if I fix f because ultimately I'm trying to come up with sort of integral of f somehow. And so if you were to think of these, all four of these things, as functions of the sampled partition, or here partition itself, these can be thought of as nets. So maybe you can write it like this. Okay, so what does this mean? I'm saying fix f and think of this Riemann sum as a function of the sampled partition. Okay? All of these can be thought of as nets. These more generalized sequences that you've seen in problem set 4, which we're hoping to release the grades of later today also. The complication is that even before going into this, I want to say a couple words. So when I say these can be thought of as nets, maybe we can discuss a little bit. So how can I perhaps make any sense out of this? So what's a net, for instance, heuristically? So a net is supposed to be a generalization of a sequence, okay? And so with a sequence, we had a notion of time, and then we had a notion of space. I'll write it like this. I told you that you should have these interpretations in your mind when you're thinking about sequences. And what was the idea? Well, time has this progression. This is my time. Goes off to infinity somehow. And for each time, if I look at where x bullet is, at that time, I have a sequence. Okay? And why do we think about sequences? Well, we would like to be able to say things like, oh, this is convergent, whatever. And how did we make sense of this convergence? Well, we said, let time run, wait some time. If after that you're within an epsilon of your target, that's convergence. Okay? So when it comes to these Riemann sums, whatever, now our time is possibly going to be branching. So I want you to think of, this is the hard part about these. I want you to think of each of these partitions as one time. Okay? And so here's my new time. Okay. Say this is this Riemann sum, taking real values. Let's say we're sort of going down. Up top, each point here should be one partition of the interval, while the trivial partition, so to speak, is a partition that doesn't divide. It has exactly one cell. Okay? So probably then, if I sort of partition it into two, I'm kind of sort of progressing time in a sense. Let's say this is the partition into two equal pieces. But of course, I could also do something like this. Maybe somewhere here. And then I can keep going. Maybe something like this. Okay? Keeps going on and on like this. What I would like to do is to each, well, I guess if I'm just looking at partitions, let's just look at all this upper Darboux. Goes into reals. Here, I attach it to this. It gives me so let's call this something. Well, this is just the partition that has exactly one element, which is the whole interval itself. But if you look at this, this is nothing but sup of f times the length of I. Okay? But then if I were to plug this partition in, for instance, into the upper Darboux sum, probably what's going to happen is this is going to shrink a little bit. And maybe, or if I do this too, probably it's going to shrink too. Maybe these two are not quite comparable. But ultimately, I have some sense of time progression. Okay? I would like to be able to say, so maybe like this. You see, my time sort of progresses. It sort of branches out, whatever, into multiple sort of further times. But I would like to be able to say, well, there is a sort of threshold. Okay? There is sort of like a sufficiently fine resolution partition such that after that, I am within a target. Say this is my target, R star, target integral. I would like to be able to say, well, after this very nice partition, no matter how my time sort of branches out into multiple sort of further times, the integral is always going to be, so the upper Riemann, upper Darboux sum is going to be always within this target. So ultimately, you want to say something like this. So somewhere here, it is not inside this partition set, but there's this infinite partition into points. This is not a finite set in general. It's still a partition, and in more complicated settings, this would be what is called the point partition. And ultimately, you're trying to associate to this partition some sort of a Riemann sum as well. But because this is not finite, then you would need to make sense of this summation over infinitely many points, which you cannot do. And so the way you do it is by approximating it using finite partitions somehow. Does this kind of make sense? The complication on top of all this is that there are multiple different senses in which you can say, oh, if I wait this much time after my integral, after that my integral is within n epsilon. Namely, we're going to look into 3 specific ones. So just like in the sequence case, I would like some structure on sPar or par that allows me to say, if I wait until this time, things happen. I go until this time. If I wait until this time, after that, good things happen. After that, I have good estimates, whatever. And so the mathematical formalism that sort of supports this idea is what is called a directed set, which you've seen a little bit. There are distinct directed set structures on these. I'll continue here. There are 3 relevant directed set structures. So one of them is in the sense of refinements. So this partition is after this other partition in the sense of refinements. The other one is in the sense of meshes. And the third is in the sense of gauges. Okay. You'll see probably the definitions of these in the next problem set. Here's a distinction, heuristically speaking. This is the directed set structure that Taylor and Tao use. This is the structure that you use in Calc 1, in fact. And the third one is used in the Fonda book, which is this Henstock-Kurzweil. Okay. These two really work for Riemann integrals. This we're going to start using for HK integrals, Henstock-Kurzweil. So these two Riemann integrals. It takes a while to get accustomed to this idea of a gauge, and we're not going to do that today, but we're going to spend next week probably talking about this. But at the very least, oh yeah, go ahead.
What do you mean by directed set structures?
Yeah, so that was also something that I had defined in the fourth problem set. So I want to say something like this. OK, I'll write the definition. Let A be a set, a directed set structure on A is, by definition, a relation on A, denoted like this, such that for any alpha, beta, and gamma in A, if alpha is after beta and beta is after gamma, then alpha is after gamma. This is what is called the transitive property. And if I have any two times, alpha 1 and alpha 2 in A, there is some time that I after both of them simultaneously. There's a beta in A such that beta is after alpha 1 and beta is after alpha 2. The standard directed set structure, for instance, on positive integers is this. Oh. Say positive integers, and this relation satisfies these. If m is after n and n is after p, certainly m is after p. And if you take any two integers, well, their max is greater than both. So this is a directed set structure on integers. You have a sense of what it means to be able to wait until a certain time and then only going forward after that. This sort of encodes the idea of a future abstractly. Yeah, this was also in P set 4. The other example I gave there was another example of a directed set structure on positive integers is, well, you could say m is after n if n divides m. That's another directed structure, for instance. See, I'll leave that to you. It's a nice exercise. Okay. Any other question? Did that kind of answer your what you were saying? Yeah. The way I think about it is that, like I said, these are supposed to be like times, and I want to think about sampled partitions and partitions as sort of metaphorical times. I would like to be able to say, I'm going to wait until a certain partition, such that after that partition, meaning once I start looking into partitions that are more refined, whatever that would mean, my Riemann sums or these upper or lower Darboux sums, whatever, they don't move too much. They sort of stabilize after that partition. OK. Now, this sort of kind of thinking is not absolutely necessary. I like it because it sort of allows one to think about Riemann sums and these kind of things in terms of epsilon deltas, just like you would do with sequence convergence. Okay. So, two definitions I want to give that I'm going to need in the statement of the next result, which is this characterization, is, well, one of them is the idea of a mesh of a partition, and the other one is what is called the common refinement. Or rather, coarsest common refinements. I don't need a function here. Let P and Q be two partitions. The mesh of P is going to be, well, the soup of all lengths of all pixels. Soup over all pixels of the lengths. It's a positive, or rather non-negative number. That's the mesh. So this directed sum is related to this number somehow. Essentially, you would say, in terms of meshes, P is after Q if its mesh is smaller than that of Q. That is to say, if the pixels of P are smaller compared to the pixels of Q, smaller in length. I'll do an example in a second. Another thing, so this is a second definition. P product Q, well, the coarsest common refinement, coarsest common refinement of P and Q is P product Q defined by the collection of all pairwise intersections. P intersect Q, where P is in curly P, Q is in curly Q. So somehow this idea has to do with this refinement. So here are examples. I is 0, 1. Okay. 0, 1. Say these are all into equal pieces. So, so P is 0 to 1 over 8, 1 over 8 to 2 over 8, dot, 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 7 over 8 to 8 over 8, so which is 1. That's certainly a partition. That's finitely many elements. And if I were to take each of the elements in this partition is a pixel, is an interval. And if I were to take pairwise intersections, well, the intersections can be at most a point. And so this is a partition. I'll ask you, what is the mesh of this? Right, so you look at each of these. What are the lengths? 1 over 8, 1 over 8, whatever. So the mesh is 1 over 8. Okay. Let's look at another one. That's my new partition. Okay, 1 pixel, second pixel, third pixel. What is the mesh? Right, so it doesn't need to be the case that each of these pixels has the same length. This is, of course, a nice situation, nice case, and probably in Calc 1 you use these, but in principle that is not needed. Okay, so you look at each of these lengths, 1 over 4, 1 over 4, 1 over 2, you take the max of these. So P is a finite set, so instead of this soup, I could have used max if I wanted. Does this make sense? Okay. So probably you see, in the sense of, in the sense of meshes, I would probably want to say, oh, this partition is after this guy, because this is like finer. Its resolution is higher. So the Riemann integral, or rather the Riemann sum associated to this, should be closer to the actual integral. That is the idea of the net, of a net. Initially, this idea of a net was, in fact, one of the main motivations why Moore and Smith, the two mathematicians that came up with this idea, the reason why they came up with it was because they wanted to sort of combine idea of Riemann integration and sequence limits, among other things. So that's one example regarding meshes. Example. Let's look at an example of this common refinement. Again, I'm going to take I to be 0, 1. Okay, so I'm going to do it like this time. So here is one refinement. One partition. Let's call it P. And here's going to be another one. Let's call it Q. Like this, like this, like this. And then let's set Q to be like so. Okay? These two are two partitions. I look at now the coarsest common refinement, P product Q. By the way, you might also see the notations P sort of veg Q, P join Q, whatever. Depending on the context, the people use like different symbols for this. There's no set notation with any of this stuff. Looking at, depending on which type of a literature you're looking at, the notation changes. So given these two partitions, I want to come up with this common or coarsest common refinement. I'm going to do that in the middle. By definition, the pixels in this should be the intersection of some pixel from here and some pixel from there. In terms of the cut points then, all I need to do is to shuffle these together. Okay. Shuffle them together, and now you have a new partition. That's P product Q. Okay. Does that kind of make sense? In a sense, this is like the more intuitive notion of the directedness for partitions, but it's in a sense harder to use in calculations compared to the mesh. And why do I call this the coarsest common refinement? Well, because you see, any pixel here, for instance here, is included in some pixel in both P and Q. This little pixel is included in this larger pixel in P and this larger pixel in Q. And furthermore, if I had, so in a sense, this is like the optimal way of sort of combining P and Q together. Okay. So here's a theorem. And don't worry if you're feeling lost about some of this. This stuff is really hard, and that's why we're covering it before we're doing differential calculus. Differential calculus is a lot easier compared to this. Formalization of Riemann integrals, it's kind of painful, at least at first. Maybe for those of you who like probability and stuff, well, another way to think about partitions is, well, these are sort of information that you can condition on. You say, assuming P, what is the probability of whatever? And then this common refinement is really being able to assume two conditionals simultaneously. It corresponds to that, really. Once you start sort of learning probability theory, that kind of makes more sense in essence. So here's a theorem. Let f be a function. And the following are equivalent. The following are equivalent. That's another common abbreviation we like using. I'm going to state them, but probably we're not going to be able to prove even the part I wanted to prove. Some of these parts probably are going to show up in the next problem sets. Let's write it. F is Riemann integrable. Okay. So this is a characterization of what it means for a function to be Riemann integrable. So far, remember, we defined a function to be Riemann integrable if its lower Riemann integral and the upper Riemann integral is the same. And these we define in terms of integrals of the step functions. Okay. Look at my notes. Okay. For any epsilon, there are two step functions. Sigma underscore, sigma over score, such that for any x in I, this guy is below f and the other one is above, and their integrals differ by an epsilon. Okay. 3, f is bounded and for any epsilon there is a partition such that the Darboux aperture associated to it is bounded by epsilon. This is really convenient. Okay. Here's 4. F is bounded, and there is a sequence of partitions whose Darboux sums converge to 0. Limit as n goes to infinity of the, or rather, the Darboux apertures converge to 0. It's 4, 5. Okay, that's the final one. I'll write it here. For any epsilon, there is a delta such that for any sampled partition, if the mesh of P is bounded by delta, oh, I should have said there is a number, R star, such that for any epsilon, there's a delta such that for any sampled partition, if the mesh of the partition is bounded by delta, then the associated Riemann sum differs from this R star by at most epsilon. What is likely going to happen is that I'm going to leave the equivalence of 2, 3, 4 to the next problem set 6, and we're going to do in class 1 and 5 are equivalent. Okay, I'll write that. So for instance, to go from 3 to 4, you just farm this statement. So these probably we're going to leave as exercises, nice sort of exercises in sup and inf management. 1 and 5, the equivalence of these two, it's kind of a nasty proof, and that's why we're going to do it in class. I mean, it's not too nasty, but it's kind of technical. Okay. I'll say one final thing. Somehow, 1 being equivalent to 3, being equivalent to 5, underneath the hood says that this refinement directed sum, directed set structure is equivalent to the mesh directed set structure for Riemann sums. Okay, that's it for this week. Thank you. I'll see you next week.